Assalamualaikum and good day. So now we are moving into a new chapter that is planar kinetics, and now we are discussing about another method which is called the work and energy. So before we begin, I would like to introduce a little bit about kinetic energy. So whenever an object has a motion, it will have kinetic energy. Okay, this I suppose that all of you should know about this already. So now we are talking about a rigid body, right? Rigid body, as I've mentioned, it has both translation and also rotation. So now kinetic energy also is divided into two types, or basically two formulas to calculate the kinetic energy. The first one is translational kinetic energy, which is calculated by 1 over 2 times the mass times the velocity of the center of gravity square, 1 over 2 mvg square. And for rotational, now if you notice, this m here, mass, is now replaced by the mass moment of inertia, okay, and also the velocity, the linear velocity, is now replaced by the angular velocity omega, right? So both looks the same. For translational, it's half mv square. For rotational, it's half I omega square. Now, we have discussed previously that there are three types of motion for a rigid body. So the first type of motion, when you have translation only, then the kinetic energy will be equal to 1 over 2 mvg square. When there is rotation about a fixed axis, now you have two terms. This is translational terms and this is rotational terms. So both you have to add these two terms and you will get the the total kinetic energy. Or if you can find the mass moment of inertia about center of rotation, okay, center of rotation O, for example, then T can also be calculated using this formula, 1 over 2 IO omega square. So that is the second type of motion, which is rotation about a fixed axis. Now, the third type of motion, as we have explained since chapter 1, is the general plane motion, which involves the combination of both translation as well as rotation. So in this case, of course, we have two terms as well you have to add. This is for translational kinetic energy. This is for rotational kinetic energy. And if you recall, for general plane motion, if we are able to find the location of instantaneous center of zero velocity, IC, then we find you should be able to find the mass moment of inertia about IC. Then you can calculate the kinetic energy for the general plane motion rigid body by using this formula, 1 over 2 IIC omega square. All right, let's look at a few examples on the calculation of kinetic energy. So in this case, we have a disk. All right, we have a center of rotation. Let's call this point O. Now this is a pure rotation case. So if you recall from our previous slides, all right, for pure rotation, we have we can use this equation right here. T is equal to 1 over 2 IO omega square, and in this case, this we have to know what is IO. Okay, now you can refer to the table of mass moment of inertia, and in this case, it is 1 over 2 m r square. All right, 1 over 2 mr square. So I think r here is missing. This should be 2 meter. Okay, so you have 900 J. This is the kinetic energy is then 1 over 2 IO omega square. All right, so this is IO, which is 1 over 2 M R square. Okay, now let's look at the second uh, type of motion, which is the rod now. Okay, basically you have the center of gravity over here. Okay, and the kinetic energy. Now, if we would like to use T is equal to 1 over 2 m Vg square plus 1 over 2 Ig omega square. All right. So then this will be the equation. So this is m, this is Vg square. So how do we get Vg like this? If you recall from kinematics, V is equal to omega times R, right? So R here, it's given, this is omega equals to 2 rad per second. So omega is 2. R is the distance from, R is basically the distance from point G to the center of rotation O. So this is R. All right. So if you see the total length of this rod is 6 meter. L, I'm going to write L equals to 6 meter. So the half here must be 3 meter, right? So therefore R is equal to 4 minus 3. So R is 1. So here you have R is 1 meter. So therefore you have 2 times 1 here. Okay. Um, that is for the first term. So this is for the translational terms. Okay, this is half, this corresponds to this term, half mvg square. And for the rotational terms, this is the rotational terms now. It's the rotational terms is 1 over 2 ig omega square, and you know that this is a slender rod. Okay, for slender rod, from the table you know that ig is equal to 1 over 12 ml square. So hence you have this 1 over 12. This is the mass. This is the total length of the rod. So altogether, when you calculate and add these two terms, you will get T equals to 800 joule if you use this equation. An alternative to this, or you can also use T, you can also use, for example, T is equal to 1 over 2 I O omega square. Remember, it's either this, you can use this, or you can use this. Okay, for the case of rotation. So now what you need to know is what is the value of IO. Okay, you need to know what is the value of IO. So IO is basically, I'm gonna write somewhere here. IO is basically, using parallel axis theorem, is equal to Ig plus M times D square. So M is the mass, D is basically the distance from center of gravity to the center of rotation. So basically D is also equal to R here. This is also the distance D over here. So you will have IO is equal to Ig, this is Ig, 1 over 12 ml square, all right, plus M is 100, and this is D square. Okay, so then you will get the same value of 800 joule as well. So two alternatives. This is number one. You can use the calculation using both terms. This is translational terms, as well as the second terms, which is rotational terms, or you can straight away use this equation, which use the the mass moment of inertia about the center of rotation, about center of rotation. All right. Now, let's look at another example. The first two example was rotation about a fixed axis. Now, can you guess what is the type of motion for this one? This is general plane motion. Why? Because you know Vg, the velocity of center of gravity, is moving to the right. So this is translation, and the the wheel here is also rotating. This is omega over here rotating. So you have both translation and rotation. Therefore, this is definitely general plane motion case. So for general plane motion, you have to use both terms also, which is T is equal to 1 over 2 mvg square plus 1 over 2 ig omega square. All right. So this is what you have. This is m, mass. This is Vg. Again, I have explained previously how do you get the value of Vg here is equal to omega times r. This is what we have learned in kinematics. V is equal to omega r. So you have omega 2 rad per second. R is the radius of the wheel, which is 2. So 2 times 2 square. So this is for Vg. And the second term is 1 over 2 Ig omega square. So this is the Ig of a thin circular disc. Ig is equal to 1 over 2 m r square. So this is how you calculate the kinetic energy, and you will get the final answer 1200 joule. An alternative to this, you can also use the second equation. This is the first method. The second method you can also use for general plane motion. T is equal to 1 over 2 IIC times omega square. But you need to know where is the location of IC. Where is IC? Okay. And here it says no slipping. Remember from chapter 2, when it says no slipping, it means that the contact point between the body and the ground is indeed the location of IC. So this is the location of IC. And therefore, you know that you know how to find the IIC. So basically, IIC is using parallel axis theorem is equal to IG plus md square. So what is d over here? What is d here is basically the distance between G, the center of gravity, and IC. So in this case, this will be the distance d, which happens to be equal to the radius of the wheel. All right, so there you go. You have this part here is Ig, okay, 1 over 2 mr square, plus this is m, and this is d square. So you will get the same answer, 1200 joule. All right, so that's how you calculate. I give you a few examples on how to calculate the kinetic energy of a rigid body in motion.